right, so in this first example here, we've got a spinning merry-go-round, right? Spinning at a constant angular velocity. And what we do, or what we're analyzing here, is somebody starting at the center and walking outward from their perspective, always walking directly outward. So from the person's perspective who's walking, whether that's you, me, whatever this person is, they're continually going outward, but they're in this rotating reference frame, right? So at any given time, right, we could have their position here, let's say, and we are moving, let's see, there and here. Now these should be unit vectors, so they should be the same length. Don't matter as much what the absolute scale is, but they should be the same length. So if I was to do this right, they would be the exact same. But let me just label this one out here where I have plenty of space. Okay, this is your radial direction, and this is your tangential direction. The person walking always goes at constant r dot, so their motion is always outward from their perspective, but the rotation of the system alone, which is always in the theta direction, pushes them that way as well. So they kind of end up heading, at any given time, radially outward together with the angular motion. So with a qualitative description of this motion, we'll get into finding an expression for the true acceleration vector here in just a moment. But let's start with a qualitative description. Okay, what qualitative means is we're not going to do any, we're going to do hand waving. We're just going to say, how do things relate? If one thing goes up, does the other thing go up? Things like that, okay? And so that's what I've just done out loud as a qualitative description without actually talking about the actual quantities related. Okay, so we know that, we're kind of verging here on talking about the quantities, but we have angular motion just generally, qualitatively, due to the rotating platform, the merry-go-round, rotating platform. Okay, and so this is the omega constant. Describes the motion. And then 2 is we have radial motion due to the walking. Due to walking outward. This breaking down into these two phenomena, helps see the concepts involved here, right? So the r dot is constant. And these things are actually completely perpendicular motions because this radial motion, this outward walking, is along the radial coordinate, and this angular motion is along the angular coordinate. So along the unit vector for change in angle and along the unit vector for change in radius. Okay, so now let's get into the quantitative description. We're actually, doing what's being asked here. Quantitative description of motion. We'll actually dig into the analytics here. Okay, so see how we're going to have all the quantities showing up here? Our acceleration vector defined here for this these polar coordinate description of motion, right, there is our radial component, and our angular component looks like that. Okay, let's see, what can we cross out here? Well, r dot is constant, so r double dot is 0. Since r dot equals constant. And alpha is also 0, since, since here omega is constant. And all alpha is the time derivative of omega, and r double dot is a time derivative of r dot, right? So those two things we know are 0. So that leads us to the final result. Let me put it over here. The acceleration vector is minus r omega squared er plus 2r dot omega e theta. Now, we could be done here. In fact, we're happy with this, right? We're in the problem statement. So r is our, as we're moving out, that's kind of the coordinate involved. We're happy with how r is, and then r dot is constant. Maybe that's imposed, right? Constant r dot. And an omega is imposed in the problem statement to a constant omega, right? So it's kind of a, we're happy with this expression, assuming that those kind of quantities are given. Now, let's just dig into this a little bit, right? So what are these terms? Okay. This here, well, actually, maybe we want to start with this one. No, let's start with this one. This is our centripetal acceleration, okay? Centripetal acceleration, okay, due to the rotating platform. Okay, related to the first point up here, okay? So this is like number... Oh, I'm sorry, I shouldn't say it's due to the rotating platform, right? It is centripetal acceleration really due to what it's provided by is the friction in the person's shoes as we have this rotating platform, right? And then this one over here is the Coriolis acceleration. Okay, and this is now a fictitious effect resulting from the rotating platform, resulting from the rotating reference frame, let's say. So Coriolis acceleration, a fictitious effect. All right, if we include it like this, basically this is not an effect that it's something that shows up in our description of the motion here, right? But it's not. It's due to. It's not something that the actual person is doing. It's just that the fact that they're in this rotating reference frame. So it's not their motion themselves. It's a combination of their motion together with the motion of the actual reference frame. So this is a fictitious effect resulting from a rotating reference frame. Okay, so we snuck that in here. Let me put a little diagram of this. What we mean by this is, let's say the person walks very fast. Okay, so they start from the center, and their goal is to get to the outside and do it in a direct radial line, right? So at this point, they move that way and they walk quite fast. I just want to be able to just, it doesn't matter how fast, but get to the edge before we go a whole way around. This one, they're walking very slowly because they have this whole spiraling effect going on. But what's going to happen is they head directly outward, but while they're walking, in that like little time instant, the platform rotates. And so they head this way, but their goal of getting straight out, they start turning a little bit with the platform, right? And then at this point, they want to head directly outward, but it continues to turn on them, right? And at this point, they want to head completely outward, but it turns. So the goal was to head directly outward, but in the end, they kind of have this curving pattern that goes with the angle, right? With the angular motion theta. All right, and that's what we call a Coriolis acceleration. Okay, so we'll see that showing up. Centripetal acceleration. Did I want to say anything? It's really due to the rotating platform and friction on the friction with the person's shoes or whatever. Friction of shoes on the platform. That's what's providing the force that would cause this acceleration. I don't know. Okay. All right, so in this second example of applying our polar coordinate analysis of kinematics here, we have a block, except we have this rotating platform, a rotating disk, yeah, a block in a disk. Okay, I thought I had those words mixed up. Okay, so we have a disk that's rotating, so like a platform, and then this block is moving outward. Now again, describing the forces involved here, like what's actually causing this motion, that's for like later on, like what would actually cause this. We just have that this is happening, so it's got this like limit on the motion in that the block can only move radially outward, and then the radial outward velocity, the speed at which it's moving radially outward, is 4t. Now you can imagine as the disk moves, right, the actual the block, at a later time is going to, as it moves outward, yes, it's going to move outward, but it's also going to be moving around with the rotation, right? So if we could do anything, you know, to just sort of, where is this thing going to go? Well, you know, we need to figure out, but it's definitely going to be moving to the left as it's moving outward. The outward motion is given to us as 4 times t, or 4 times the time. Right? Okay. So now, and then we got a constant rotation rate given here. Okay, so when we go to analyze this motion, we want to analyze, you know, where this thing is. We're going to do it in polar coordinates. So if I sneak in here right alongside our r dot, right, that is your radial coordinate, and then perpendicular to that in a positive theta change direction is the angular coordinate, right, where this is our theta. Okay, let's see. Oh, another thing. Oh, I don't know if I have space for this to add in there. I can probably sneak it in somewhere. Oh, we can do it like this. Off to the side, to the origin, right? This now, right, is the radius, and what's unique here, we don't have circular motion. The block isn't under circular motion because the radius, the actual magnitude of the radial vector, is increasing in time, right? Given r dot. So this is not circular motion. In fact, it's going to kind of spiral outward. All right, this block is going to spiral outward. All right, as before. Okay, let's get into it. So let's see what's actually given to us. Let's like lay it all out here. We're given that r dot, which is the radial speed, is 4t. So our radial acceleration, the direct radial acceleration, is 4. Okay. Omega is given to us, that's theta dot, right? The change in theta with time is 6, as given. And so therefore our angular acceleration, which is omega dot, or theta double dot, is 0. Derivative of 6 is 0. Okay. We want to know the velocity and acceleration magnitude only at a given time of 1 second. So let's go to our velocity vector, which is r dot e hat theta plus r omega e hat, or sorry, r dot er plus r omega e theta. So that's going to be 4t e hat r plus 6r omega 6 e hat theta, right? These little r's, these are r and t itself are variables, right? As t changes, radius changes. So we need to determine what is the radius r of our block, what's its different distance to the origin, O there, at time 1 second. Once we can do that, we'll be able to determine what the velocity vector is. Okay, well, r dot is dr dt. Okay, that's what's given to us, and so that must equal 4t, right? So we just need to solve this for a relationship for what is the radius through time. Well, we can do that through integration, right? dr 0 to r equals, so the thing about this is separating the variables, so pull the dt over to here, or multiply both sides by dt and then integrate in time. Well, this is just going to become the dr integration, and then over here we're going to integrate in time from 0 seconds to 1 second. Okay, so our radius, now this is going to be the radius at time equal 1. And I guess, again, we do need something like one more specification. A block initially at rest at O. Okay. So that at time 0 we know to start our radius at 0. Okay, so that's why we were able to put that there. That does need to be specified. I just didn't fully, I took these problems and these sample problems, and I try to simplify the problem statements, but keeping as much information as we need, and I left that one out. All right, so our radius then at time 1 second, from starting at the origin at time 0, is going to be 4t squared over 2 from 0 to 1, which is then r equals 2 meters. Okay, so all we need to do now is at time 1, plug in t equals 1, our radius is 2 meters, plug in r equals 2, and we've got our velocity vector at time 1, which is 4 e hat r plus 12 e hat theta. These are in meter per second. And so our magnitude is, take the first component squared, second component squared, and square root the summation there. 12.649 meter per second. Okay. All right, let's do now the same thing for acceleration. So this was velocity. I say the same thing, right? It's definitely going to be different because acceleration is always a little bit more complicated. Usually all of our relationships have extra terms in acceleration, but let's start with just writing all the terms out. R double dot minus r omega squared e hat r plus r alpha plus 2r dot omega. That quantity is times the angular unit vector. So first thing, right, that guy drops to 0 because our angular acceleration is 0, because omega is a constant value of 6. But everything else we have values for. So r double dot we've already determined is 4. R dot, which shows up in the e theta term, is 4t. You know, we basically have all these things, right? So we're just plugging stuff in, and it should flow pretty naturally, right? We're doing a check, though. Do we need to determine anything else? And I think we have values for all these quantities at the time we need it, which is t equals 1. Okay, so r double dot is going to be 4 always. And then we have r itself is the 2 meters. And our omega is always constant 6. That is in the radial direction. Plus 2 times r dot is 4t, so this is going to be 4 times 1. And then omega is 6. And all of that, these are all multiplication there, e hat theta. Okay, so a1 is then, this is going to be 4 minus, so 36 times 2 is 72, subtract 4 off, well, that's negative, and then we add that back on, so negative 72 plus 4 is negative 68, and then we have 4 times 6 is 24, times 2 is 48, e hat theta. All of this, our units are meter per second squared, and so just another magnitude to take of this vector. 68, okay, let's be really careful. Minus 68 squared plus 48 squared square root is 83.235 meter per second squared. Okay. So this is nice, right? These are not, this was not a purely, circular motion example. Okay, that's it for polar coordinates. We're going to use this, going forward when we get into kinetics. But next up is to wrap up this kind of, focus on particle kinematics. We just need to extend this to talking about like relative motion. And then soon enough, we'll be talking about the forces that cause these motions.